let's say we have made this regression and we have the slope, the beta 1 hat, and we have gotten an estimate of the intercept. And what we want to do when we do regression analysis is to find whether or not there's a relationship, or we just want to investigate the relationship between the x variable and the y variable. So, for example, we have some questions we want to answer, like, is the observed relationship between x and y and the sample strong enough to conclude that it also holds in the population, for example? Or how can we use the sample statistics of our estimated intercept and the estimated slope to determine a plausible range of values for the true intercept and the true population slope? So this is the idea behind hypothesis testing, and to be able to use our sample estimates to say something about the true values, we need to know the dispersion around the dispersion of these estimates. And you might think of the estimated intercept and the estimated slope as constants, of which they are not, because the true population parameters, they are constants because they are constant over the whole population. So if we had data for the whole population, then we could fit our regression line and find the true values. However, we need to what we are able to is to take samples from the population. And whenever we take a sample and run a regression, then we get one result. If we take a new sample and run a regression, then most probably we would get a different result for the intercept and the slope. So whenever we take new data from the population, we will get some estimate of the slope and the intercept, and we can record these and put them in a certain, or we could form like histogram of our estimates, and the more estimates we have, the more normally distributed this histogram would look. So what we have is that the true, for example, the slope, the true slope, the population slope, would have a certain value, whereas our estimates would be in a range around this true population population value. Okay, and because of the central limit theorem, this is normal distributed. Let's say I can write this properly. Properly distributed. Okay, normally distributed. Okay, and what is normally distributed? It's the estimates which are normally distributed, and because they are normally distributed because of the central limit theorem, then we can kind of give a measure of the uncertainty based on the standard error. And think of the standard error just as the standard deviation of something. So, for example, the standard errors, they describe this dispersion you would see if you take many samples from the population data. Okay, so how do we calculate this standard error? If we have a simple regression model in which we have only one x variable, then we have this quite simple equation to give us the standard error of the slope, for example. And this equation, you have the n, which is just the number of observations, which means that the denominator here is just the number of observations minus 1, because we lose 1 degree of freedom, and you just take the positive square root of that. The Sx is just the sample standard deviation of the x variable, which is simple to get, right? You just type in, give me sample standard deviation of the x variable, and you get a number, right? The most tricky one is this one. Okay, so what is that? It's the standard error of the regression, which sounds quite advanced, but it's really not, because this is just the sample. I need to move my pad. Sample standard deviation of the residuals, right? So whenever you do the regression, you get this line, and you have x and y, and you just look at the residuals here, and you just calculate the sample standard deviation. And most statistical software give you, or all statistical software give you these or data structure with these residuals. So this is also quite simple to get, right? So note that a smaller standard error of the slope means that your if we go back to the estimate here, a smaller standard error of the slope means that your estimate is more certain, right? And a larger standard deviation of the, or standard error of the slope means that you are not certain in which area the true population value actually is. So we have some features of this standard error. It is that as the standard sample standard deviation of the residuals, the SU hat falls, the standard error of the slope falls. And you can see that you can see that because if you have like y hat, if you have a very small standard deviation of the residuals, then you're quite certain where this regression line goes. Whereas if the residuals have a large dispersion, then you really don't know if the line should be here, or maybe like this or this, which means that as the standard deviation of the residuals falls, you are more certain of the model slope itself. Okay. Another thing is that as n increases, which means that if you have more data, then the standard error of the slope falls, which means that the more data you have, the more certain you are on where is the true slope parameter, right? So and you can see that from the equation in on the last page. If you increase the denominator here, then you reduce the value of the fraction. Okay, and lastly, as the standard deviation, or the sample standard deviation of the x variable increases, the Sx, then the standard error of the estimated slope falls. And just to get like a visual intuition of this, you can see that if you have these blue dots in the middle, they have a low standard deviation, right? And whereas the black dots, they have a larger standard deviation. and if you are trying to just draw a line through either of these two sets of points, then you would be more certain to have the correct slope if the points are far away. Okay, so that would be the visual intuition behind it. Well, and the mathematical intuition is that as you increase the denominator here, then you would reduce the value of this fraction, which reduces the value of the standard error. Okay, so that would be some of the features of the standard error of our estimated slope, and the estimated intercept also has a formula. You can find that in the textbook, because we focus here on the relationship between a change in x and a change in y, because we often look at can we use the x variable to explain any of the variability in the y variable. Okay, so and in practice you don't need to actually remember this, but it's nice to know. in practice, statistics software will calculate this for you. Okay. So, the three approaches for hypothesis testing we will construct in this course are actually the following. So, what we want to do is to make a confidence interval, which means that we make a band around our estimate. We also want to make a test statistic just to measure in standard errors how far away are we from our null hypothesis. And we are going to look into the p-value, the probability value. Okay, given the distance between our null hypothesis and our estimate, what is the probability of getting something more extreme on average? No, at random. Yes. So, but before we turn to the mechanics of this, I want to just show you what hypothesis testing is about. Okay, so for example, we want to say something about the population, but we only have our sample estimate, right? But given the central limit theorem, we can use the fact that these estimates are drawn from a normal distribution, right? Which means that what we do is that we have the I've shown you before the beta 1, okay, the true beta. We draw a sample. We know that if we draw enough sample, we can make like this histogram around the true value, right? We can make a histogram of all our beta hats, our estimates, and this would be normally distributed. And what we also know is that this is normally distributed with a standard error as we calculated previously. So this would be one standard error below, and this would be plus one standard error above, right? Plus one. And if you go one standard error below and one standard error above, in this interval, you would get about 68% of the estimates, right? If you go two standard errors above and below, minus 2 standard errors, then you would capture about 95% of all the estimates of the slope, right? Okay, so now we know this, but what you can do is that because this distribution, it's symmetrical, okay, normal distribution is symmetrical, you can use the fact that if you have, I'll just make a new drawing, the true beta here, right? And if you, this you cannot see, okay? This is invisible for you. What you can see is the beta hat, right? So this is your estimate. But how do you find the probability of getting something more extreme than your draw, right? Because you can't see the true beta, but what you can do is the one point, the probability of this tail, like getting something above or more extreme on the positive side, is just the area under this curve, because underneath a probability curve, the total area is 1. Okay, so the 68% area here is just an area of 0.68, right? Okay, so what we can do, because this area is of importance for us, it's the probability of getting something more extreme than our draw, right? On the positive side, it's one-sided. You can also have a two-sided test. Then you just add the areas under the curve. But what you do is that you just shift this normal distribution over to center at the value of your beta, or your estimate, right? Oops. Let's see. We'll just take this again like this. Okay. Why can you do this? Why can you do this? It's because the area here underneath this graph is the same as the area underneath this one. Do you see that? Because this point and this point has the same y value, right? Or the same altitude, which means that the graph, or the area under the graph, which means the probability under the graph, is the same. This is an under-communicated area of hypothesis testing. This is why we can use the standard error to say something of the probability of getting a certain value, or the probability that we actually capture the true value of the population, even if we cannot see the true value of the population. But what we do is that instead of inputting this beta, we input our null hypothesis. Okay, the value for our null hypothesis. So then we can see, is our estimated slope different from our null hypothesis, given this dispersion of our estimates. It will make more sense in the next video, because then we are actually looking into how we calculate these probabilities. So see you next time. That would be learning by doing.